Hi, Professor Fong. I think you're muted.
Yes, you're right. Hi, how are you?
Good, how are you? So you want to join this session?
Yeah, I want to just join the sessions.
Oh, awesome.
And
Awesome.
yeah, thanks for allowing me to attend
Oh,
your.
no, I appreciate it. I know it's not easy to navigate all these technologies, so I'm worried which one you will attend. But
Okay,
yeah.
right.
So I'd like to let you know, I mean, the session is automatically recorded. So we are being recorded right now. So I think
Oh, okay,
we
that's okay.
discuss something after, right? So that the students won't get to see this. But
Right, right.
we will start in 10 minutes. Is that okay?
Okay.
So
Yeah.
I just want to let you know I'm here. So, uh, I will mute myself and stop the video for now, and then we'll start at 12. Would that be okay?
Okay, sounds good. Sounds
Okay,
good.
thank you,
Yeah,
Professor. Appreciate
right.
it.
Okay.
All right, so I think we can get started. Dylan, you have any questions? All right, cool. So, all right. So where we're left off last time, right, is that we were discussing about the Greeks. Okay, which basically, of course, right by now you get probably tired of hearing it, but this they are the partials, right, of the option value. So partial derivative, yeah, partials of the option value with respect to, right, the parameters of the model, right? So what we're interested in, right, was to show that, so in particular, we have three quantities: the theta, which is the partial with respect to the exploration with a minus sign, right? So this is tau is time to expiry. And then we have the delta, right, which is the partial with respect to the underlying stock price, and the gamma, right, which is a partial with respect to the second derivative, right, which is the second derivative of the option value with the underlying, or this is the sensitivity of the delta with respect to the stock price. Okay, so the point we were interested in, right, from last time is there is a connection, right, between these three quantities via the Black-Scholes PD. Which says minus RV plus V sub t, okay, plus V sub x, R times x, let's say R times S, plus 1/2 V sub xx sigma square S square is equal to 0, okay? So where, right, V here, right, V sub t is what we mean by theta, V sub x is the delta, and V sub xx, right, is the gamma, all right? And so what was interesting, right? So first of all, we show that this equation holds for European put and call. Okay. What actually happens, right, is that this equation holds for any European option, okay? This actually holds, right, for any European option. So in other words, right, if you have any option of this form, the payoff, right, is phi of VT, phi of ST, sorry, at time t, all right? Any function phi. Then when you compute, right, when you compute the theta, the delta, and the gamma of the option, right, and then plug them into the equation at any time moment, you add them up, or you get 0, all right? So that's kind of a remarkable thing, because in general, right, we mentioned that these guys are quite hard, it's not easy to compute them out explicitly, all right? We verify this equation by having explicit formula for the Greeks. But if we don't have the explicit formula, then how do we even check that this holds in the abstract to begin with? So that's one remarkable thing. Another, right, is that the consequence of this equation hold, right, is not just about the connection of the Greeks, all right, of these three Greeks, but the implication of this is an equation that has connection with how the portfolio, all right, on the derivative and on the stock evolves. So this has connection with the hedging portfolio. For the European option. Okay, so what we mean is this. What we will show a self-financing portfolio that holds delta T shares of S at time T, okay? And starting an initial value V0, meaning the initial value is the value of the option at time 0, okay? So starting out, basically, you as the option seller receive V0 from the option buyer. You will go ahead and invest delta 0 into the stock market, and the rest you deposit in the saving account, okay, or the money market account, and you keep on doing that for each time moment, okay. And if you do so, then this portfolio, right, will perfectly replicate the value of V at time big T. In other words, right, the value of this portfolio, this will be this portfolio, right, will have value VT at time big T. Okay. So it is, so this is quite an abstract result, but I hope you appreciate the, you know, the kind of like the complexity of it and the implication. First of all, right, remember to have portfolio value, to have value V big T at time T like this, right? Because VT is random, okay? What that means is you must match the portfolio value with the value of the option for any scenario, right, that happens in the future. Now, in the context of Black-Scholes model, right, we're in a continuous space, right, setup. That means that you have infinitely many, right, scenarios to match. What this assertion says is it doesn't matter whichever, right, scenario that comes up among those infinitely many. Unlike our binomial model where we only have finitely many outcomes, right? Here we have uncountably many outcomes. Doesn't matter. We will get this value, okay? Now, of course, right, so that's of interest, kind of mathematically, but like I mentioned, in practice, right, you will not be able to hold exactly delta T at any time moment, simply because here, right, T is a continuous variable. Okay, so you will not be able to do so, I mean, physically. But even if you try to approximate it, meaning like you try to, you know, do each day hold delta T shares of stock like this. So you should realize that that's what you're doing is delta hedging, or try to make the portfolio, right, delta neutral. But on the other hand, right, what even in that approach, what prevents you from completely being successful is the transaction cost, right? Because when it's not like cost free for you to go ahead and buy share and sell share in the market. So if your interest is just perfectly replicate the portfolio value at time big T like this, then you will pay a price, right, for doing your transaction costs. And so all in all, right, I mean, this is a good scheme to have in mathematics, right, in the model. But in practice, I mean, there are different considerations that have to go into, you know, like making this happen. But it gives a good foundation for saying why delta hedging, all right, or making a portfolio delta neutral is a good idea to begin with, all right. So that's the point. Any question on this? All right. So how do we go about doing this? All right. So first, the first point we want to talk about is the dynamics of a self-financing portfolio. At time, in continuous time. Okay. So what portfolio do we have in mind? The portfolio we have in mind is going to be, let's say we have a portfolio, all right, consisting of let's say, okay, I think alpha shares, alpha T, okay, shares of stock, beta T in cash, and let's say, some external funding level, okay, C T, and then maybe another asset, like let's say a derivative, one share. Or, let's say gamma share, okay? Gamma T share of the derivative, VT, okay, V. All of this at time T. Okay. The question is how, okay, so this is the time moment T. How does the portfolio change value in the next like split second or so? So here, right, the portfolio value, let's call it pi T. What is the value of a portfolio at time pi T plus dt in terms of these quantities, for example, and in terms of their change? Okay, so actually, right, the whole idea is when time move like this, okay, when time move like this, the composition of the portfolio does not change. I mean, so for example, right, that when at time T, you hold alpha T, right, beta T, and gamma T in terms of your stock, cash, and derivative, right? It will stay the same at the next moment because you did not have time to update your portfolio yet. Okay. Your external funding will change now, right? Because that's something coming from outside. For example, it could change like this. It could go from here to here. So all in all, right, you see that your portfolio value at time T plus dt will be the old composition, but with new update. So it will be alpha T share, right? But at time ST plus dt, right? With that stock price value. Beta, right? Cash, what will it change to? It will earn, right, some interest. So will beta T, let's say, earn interest with rate R, right? 1 plus R times dt. Because that's the interest rate that's earned in that time period. And then the gamma, right, the share will be the new value of the derivative at that time. And then plus the new level of funding, wherever that is. Is that okay? So what were the dynamics, right? Dynamics means the change in the portfolio value going from here to here. So in other words, the difference, right, the change in portfolio value will be what? Well, it will be, right? So obviously pi t, right? Obviously pi t, let me rewrite this. Pi t will be all of these things, but at time dt, at time t. So pi t, right, the portfolio value at time t will be alpha t st beta t, gamma t, vt, ct, right, like that. So in other words, right, the change in the portfolio value will be alpha t, right, st plus the change in the stock. The cash, right, portion is just beta t times rdt. That's the interest that you earn. And then gamma times vt plus dt minus vt, and then ct plus dt, sorry, minus ct. Okay, like that. So, question here? And so if you push this to 0, right? If you push the time interval, right, to 0, what we get is the dynamics of the portfolio change like this. d pi t is alpha t dst plus beta t rdt plus gamma t dvt and plus dct. Where of course, right, these are just denoting the change in each of the component as we push time to 0, the time interval to 0. All right. And so this is any generic portfolio. Okay. This is any generic portfolio will have this dynamics. In other words, the change in portfolio values like this. Subject to, right, this is the holding of the portfolio at time little t. So self-financing means that you have no external funding. And by the way, right, I think when I say DCT, when I say CT like this could be also your consumption, meaning some people may decide to take money out of their portfolio, right? So external funding or consumption, this can all be captured by this quantity, which actually doesn't matter because here, if it's self-financing, that means you are not allowed to put in, right, pulling in external funding or taking out money by consumption, okay? So that's what self-financing means. No outside funding or no consumption from the portfolio itself. And so basically, right, the message is the dynamics of any portfolio investing in stock, cash, and derivative, that self-financing will be like this. The message is the change in the portfolio value in a short time interval will result purely from the change in stock price, interest rate gain, and change in derivative value. All right, question. So why is this important, right? Several reasons. First of all, remember, right, under the Black-Scholes model, what we get is that the dynamics of the stock price, right, is RSTDT plus sigma STDW tilde T. Okay. So if we can express, right, if we can express the portfolio, right, in terms of the change of portfolio value in terms of change of the stock price, then by the Black-Scholes formula, we can plug this in and get the dynamics of the portfolio in terms of the dynamic of the stock to begin with. So that's one thing. Another thing is that, right, what is the dynamics of the change in the value of the option? Okay. So remember, another point is this, that if V is a European option, a big point in our class that the message is that then the value of the option at any time t will purely be determined by the time and the value of the stock at that moment. Okay. So in other words, right, being a European option means the value of the option at time t is completely determined by the stock value at that time and the time moment. Okay, and obviously, right, for example, in terms of Black-Scholes, right, in terms of, let's say if the option, right, if V is European option, European call, then dv, oh sorry, then Vt, right, is St nd plus minus K e to minus RT nd minus, for example, right? So the function is this function right here, right? Where St shows up here and nd plus and d minus, right? Okay. So what that gives us is that the dvt here can also be expressed in terms of its delta, gamma, and theta by Ito's formula. By Ito's formula, okay, dvt dt plus v sub x, sorry, dst plus 1/2 v sub xx, the quadratic variation of s, which, if you remember that the stock price follows this dynamics, then it's going to be Vt dt plus Vx. Okay, I'll leave the st for now, but it's this. And then plus 1/2 Vxx sigma square st square dt. All right. And of course, if you want, this is going to be the theta, right? The theta of the option, the delta of the option, and the gamma of the option. Okay. So point being is this, right? That the dynamics of any portfolio investing in stock, cash, and the derivative, right, will be related exactly, you see, by Ito's formula to the Greeks of the derivative in this way. And so what's our control, right? Or what can we do as an investor? Remember, as an investor, you get to choose how many shares you invest in each of these. Gamma will be 1, because that's you sell 1 share or you buy 1 share, all right, of the derivative from the market. So gamma t, right? Gamma t will be 1, because that's the context of what we're discussing. You buy a share, sell 1 share of the derivative. What we're interested in is choosing alpha t is our choice. Is that okay? Alpha t is our choice. So you choose how many share of the stock to invest into the stock market. All right. And the claim, right, again, going back to what we're claiming, is that if this portfolio, right, holds delta t shares of the stock at time t, then it will perfectly replicate the value of V at time big T. All right. And so the point is that if we choose the number of share alpha to be this, then the portfolio we're building, right, because we are holding already, actually here we minus delta because we hold 1 share of stock. Or if you want, gamma t will be -1 because you're short selling, for example. Okay, let's do it like this. You're short selling 1 share of the derivative. Then, right, if alpha t is equal to exactly the delta of the stock, the delta of the derivative, this delta, then, right, the portfolio value in the end will perfectly balance out, which means it's going to be 0 because you are short selling one share of the derivative. We will show this. Okay, we will show this. Any question about this? It's just too much information. You're kind of getting the connection between these ideas, or yeah. So it's a lot, right? To kind of put together. So do kind of tell me if there's any point you want me to clarify. So the point is this, right? Again, the point is this, that the new object we're introducing is this portfolio right here, okay? This portfolio right here. Put yourself in the position of a trader who just short sell one share of the derivative, okay? You just sell to someone a call option. What do you have to do? You must invest in the stock and cash market to make up for your position in the derivative, okay? And the math that we're doing right here is basically an analysis of how your portfolio will change in terms of value based on the dynamics or the change in the stock price given by the Black-Scholes model. And then, right, our claim is this, that you know everything, you as an investor know everything about how the stock price will change. You know how the derivative will change because you know the derivative theta, delta, and gamma. All right. Now, of course, that's a lot of work to figure out in real life, but theoretically, you know these quantities because you know the payoff function. You know, basically, you know, for example, call option, you know how it works. So putting all these pieces together, you as an investor, sorry here, right, will see that the right choice for you to put is the alpha going to be minus. Oh, sorry, alpha will be exactly the delta of the stock, delta of the call option. Okay. Still digesting? Shall we continue? All right. So yeah, I mean, of course, the math, like, you know, you can review it, right, later on. It will fit together. Don't worry about it, right? But yeah, just get the idea of what is it that I'm trying to show you right now, okay? What I want to show you, right? I want to show that if with the choice of alpha t, which is delta t, okay, and gamma t to be -1, then the V big T, right, the portfolio value at time big T will be exactly V0. Okay, then what do I want to say here? Well, let me just put it, and okay, pi 0 equal to V0, okay? So initially we invest with this much money we got from the, sorry, pi 0 equal to 0, sorry. Then pi t equal to 0. Yeah, okay, that's what I want. Okay. So so let's explain this, right? So gamma t equals to -1 means you short sell one share of V, right? Okay, short sell one share of V. Pi 0 equal to 0 means what? Means that you receive V0, okay? You receive V0 from the selling of the derivative. But then you invest it, right? You invest the V0 into the stock and cash. So basically, nothing comes out of your pocket at time 0, okay? And if pi t equal to 0, right? Pi t equal to 0 at the end, why is it perfectly hedging? The reason is, right, pi t in the end will be, you know, some composition, right, in terms of your cash and stock. and then you have minus VT, right? That's what pi t equal to 0 at the end. And if it's equal to 0, then that means your cash and cash plus stock position is exactly equal to the value of the derivative that you need to hedge, okay, in the end. So that's the idea there. Is that okay? Okay, cool. So let's proceed, right? How do we proceed? The proceeding is a bit like, like kind of messy by unfolding this guy, right? By unfolding this guy and show you, right, that basically with the choice of alpha t equals like this, everything will cancel out nicely. All right. So let's see how that works. So the change in the portfolio value will be alpha t, okay, change in stock, beta t, interest rate gain, and then gamma t, which is -1, right? So let's do this. Let's do this, gamma t dvt. And so first, right, alpha t we say is going to be the delta of the stock. Oh, sorry, delta of the call option, the delta of the option, so delta t, all right? Let's do dst like this. And then beta t rdt, okay? Gamma is -1. What is the change in the option? The change in the option is right here, right? So let's put that in. Theta t dt plus delta t dst, and then plus 1/2 gamma t sigma square st square dt. Okay, like that. And notice, right, what's going on here? What's going on here is that this and this term exactly cancel out. This term, by choosing, right, by choosing the number of share you hold as the delta of the option, right? When you're unfolding how your portfolio changed, the fluctuation of portfolio due to a stock component completely get canceled out. So in other words, right, this will be exactly just pi t beta t rdt, right, minus theta t dt minus 1/2 gamma t sigma square st square dt. Okay. And what is, right, so the last question is, what is, so one observation, right, is that the portfolio, right, the change in the portfolio is the fluctuation from the stock price change is cancel out by the choice of alpha. Is that okay? So that's one thing, right? The second thing we want to show is what happens with this, okay? What happens with this? And this actually will be handled by the Black-Scholes PD. So I haven't showed, right, the Black-Scholes PD yet, okay? I haven't shown you the Black-Scholes PD yet. But the Black-Scholes PD is this. And so after we unfolding what the beta terms is, and we plug in the Black-Scholes PD, you will see that this term also cancel out, okay? So now the point is, if you choose alpha t to be the delta of the option, then the fluctuation from the stock price cancel out. And then remember that the rest of the component are just the Greeks of the derivative, okay? So the Black-Scholes PD says that minus R, right, times the value of the derivative, plus, what do I call it? Minus RV plus V sub T plus V sub X, right, times R times torque. Okay, and then plus gamma. Sigma square S squared is equal to 0, okay, for any option. Okay. So, okay, I think I know it's a lot, right, of symbols going on for you, but let me ask, what is this beta T term right here, right? I said we choose only alpha, right? We choose alpha. But why don't I say we choose beta? What is beta here? What is this mysterious term beta here? And correct, but why don't I choose it? Or what is it? Is it free? What is it in terms of this whole, you know, mysterious scheme of constructing a portfolio? Right? I mean, am I hiding something from you by saying that we don't touch on the beta? Exactly, right? So we choose to balance the portfolio. In other words, right, beta T, right? The whole point is that beta T is automatically chosen because alpha T, right, times ST plus beta T will be the total portfolio value. All right, which is what? Sorry, I missed something, right? Plus VT, because we have one minus VT is equal to portfolio value, right? Because that's always a portfolio, right? Summation in stock, cash, and then subtract 1 from the derivative is equal to portfolio value. So in other words, right, the beta, right, beta T is equal to pi T plus VT minus alpha T ST. All right, very good. So it's automatically determined if you choose alpha T. If you choose alpha T, like the beta T must be, you have no choice on it. So plug this quantity, okay? Plug this quantity into the beta T. All right, plug this quantity into the beta T. So, all right, let me rewrite that, all right? So we conclude that the change in our portfolio will be, right, beta T R dt minus theta T dt minus 1/2 gamma T sigma square ST square dt, all right? From, sorry. 1 second, my iPad is freezing. Yeah. So, all right. And so now we plug the beta into here, which is, right, pi t plus vt minus alpha t st, right, r dt. Or, by the way, right, what's alpha? Alpha is delta, right? So maybe let me do that again. Is equal to, right, pi t plus vt minus delta t st. So that's a delta. Okay. And then minus 1/2 gamma t sigma square. I forgot the theta, right? 1 second. Minus theta t dt minus 1/2 gamma t sigma square st square dt. All right. So Now, just stare for a little bit and try to see. This is a Black-Scholes, right? Which we did not prove yet. All right, I owe you that. But this is true, right? Assuming this is true for any, this is S, right? For any, right, derivative, which works for our case, comparing with this, what do you see? This is plus RV, right? Minus theta, minus 1/2 gamma, right? And then delta TRS is right here. So it's exactly, right, the Black-Scholes in reverse, right? The Black-Scholes in the negative sign. So this, and this cancel perfectly, all right? Which gives you pi t r dt. Do you see that? So assuming, right, all the Greeks of the portfolio interacting nicely as the Black-Scholes PD say that it does, then every component right here cancel out, and we got simply this. Question on this. Right, so first let me ask you, right, what does this mean? What is the message here? What did we conclude in the end? So the conclusion actually is very, very simple, that pi t now behaves like a saving account. Okay, pi t, your portfolio behaves like a saving account. So long story short, right, what is the whole story we've been trying to tell so far? The whole story we've been trying to tell so far is this, that you have a portfolio, okay, with delta T share investing in stock, the rest in cash, like you said, just balance portfolio out, shorting one share of the derivative. So if you choose it, if you do it right, in other words, if you choose exactly this amount of stock to hold at any time, then your portfolio is nothing but a fancy saving account. Then your portfolio is nothing but a fancy saving account. By fancy, I mean you do a lot of action, but the net result, as we show, is that it's no different from a saving account. Okay. But so is there any point here? What's the point of doing this while you have a saving account available to you right elsewhere? The point is this, right? It's not you're doing a lot of work to recreate a saving account. That's not the point. The point is by doing this, exactly the point that we have shown is that we have hashed all the risks away. Exposed to by short selling the option away by investing correctly into the stock market. Is that okay? That's the goal, all right? So the point is this, that it's not that you are interested in a saving account exactly, but you right, you have to sell, you have to service your customer by selling this option. So by selling this option, you expose yourself to the risk. So remember, right, to hedge the risk means to somehow transform all this randomness into a deterministic factor, or into, turn all this, make all this randomness disappear. So, right, exactly by, you see, by investing in the stock market and cash market in the right way, meaning do delta hedging, then all the return of your portfolio comes back to the cash. So you have no Brownian motion component, right? If you want, there's nothing like this. Zero Brownian motion component. The fluctuation, right, the noise of the market caused by the Brownian motion does not enter into your portfolio at all. It was canceled out by exactly right here, by exactly the canceling out of the DS right here. Okay. All good? Okay, what is it that you lost conceptually? Like the point of the derivation? So, okay, so first of all, right, conceptually, this is this. So conceptually, right, one thing I did not address is that first, Black-Scholes PD always hold. I did not address this, okay? So to be addressed. But barring this, right, barring this, again, right, the story is that at time zero, okay, at time zero, okay, you sell one share of V, okay, to someone. And so what your obligation is at time big T, you need to pay this person back VT. Is that okay? This whole thing is reflected by the minus VT position in your portfolio, because you owe him VT at that time big T. All right, fine. So question, so 2, right? Task. How much to invest? In stock and cash. To be able to pay VT at time T. All right. And so now you say, why not just hold BT? But beta T is just the cash position, right? Holding cash position alone will not balance out the fluctuation caused by the derivative, because the derivative fluctuation is directly tied to the stock fluctuation, right? This equation actually is very informative if you look into it. Here, basically, right, the fluctuation in the derivative is directly tied to the fluctuation in the stock by the delta. That's exactly what it's telling you. So if you claim that you only play around with the beta, then all you can control is the time dimension. You cannot control the stock dimension. And remember, right, risk to us is not really the time dimension. The time dimension almost like is like interest rate kind of thing. The stock dimension, if you're still exposed to it, then you will owe money depending how the stock behave. Does that make sense? So exactly the alpha here balance out the stock position for you. I'm not sure if that's what you're conceptually missing. Do you understand? Or still like what is it? No, Dylan. Really, just think about it. If you only hold cash, right? Actually, exactly. I think you did say, right? The risk is from short selling. Okay. So suppose you hold only cash. All right. I don't care how much cash you owe. Then the the progression of your cash position overall will be like this. You know, earning interest rate with some position, adding it from 0 to t. But in the end, right, VT will be a function of the stock, which has a Brownian motion component in it. How how can this and this balance each other out? And that's why I question you. I don't know what you mean by the end result is the same, right? If you want, mathematically, these two are very different in which way? This is very smooth because it's a dt integral, right? This is nowhere differentiable because it's something to do with WT. So mathematically, these two cannot be balanced out to begin with. Oh, right. I know. So you are asking what I was trying to address before that, you know, what is the point of doing this? Okay, what's the point of doing this? If you're just looking for a saving account, then go to the bank and just save money. But that's not the point, right? The point is this, like, there's a term called market maker, right? Market maker, in out there in the industry. What it means is, you know, someone who has a desire for some option, who knows, some V, they cannot find it on the market. Okay, so they go to the market maker, they go to you, and they ask you to sell them such an option to do business with you. Okay, now if you don't sell them that, then what I'm trying to say is your job is to sell your client this V and to get some commission in between. You understand? So you have no choice but expose yourself to this risk. You understand what I'm trying to say? It's not like you just like have nothing better to do and you just want to expose yourself to this risk. The client goes and buy. Exactly. So you are exposed. That's not a question. The question is, how do you get yourself out of this exposure? Is that okay? Yeah. So that's the value of this calculation. Is it gives the trader a guidance on how to actively trade to get rid of their exposure to all these positions. Now, why they have no choice on getting exposed to these positions because that's their job. They are making the market. All right, their job is to balance out this position. If you think of it like this, right? Another way to look at this is you're synthesizing this option for the buyer, right? The buyer cannot buy this option by themselves because there's nothing out there for them. You as a trader have access to all this fancy trading thing. So you can synthesize by trading actively and then mimic the effect of the option for the buyer. And your value is right there. Your value is, bring in this product, right? You heard of the term financial engineering, right? Ever wonder what engineering means? Engineering means here, right? You're making this product. You are bringing it out, right? You think about it. Why would anyone want to sell a call option to you to begin with? What's in it for them, right? So the job is to bring in this product, right? And of course, when they bring in this product, they must figure out how they can protect themselves. Okay. All good. All right, cool. So now, I guess let's round down the discussion, right, by addressing the Black-Scholes PD. So now what's left? So above, right, what I've been discussing so far, right? So far, what I've been discussing is accept the Black-Scholes PDE, show that the hedging portfolio, perfect hedging, okay, perfect hedging is possible via delta hedging. But this is in theory only, all right, theoretically. In practice, there are many things that we need to consider. Okay, so now I need to show you why Black-Scholes PD is true. Okay, I need to show you why Black-Scholes PD is true. So the idea of Black-Scholes PD, believe it or not, is again a play on the portfolio investment. Okay, so the idea is this. The idea is still a portfolio, but the idea is this: that we construct. So we construct a portfolio, okay, with, let's say, alpha t, right, share of S, one share of V, any V, right, and self-financing, okay, so the beta is determined. So beta T in cash position is determined. Okay. So same thing as before, believe it or not. But the twist is like this, right? And by the way, the alpha will be the delta again. But the twist is like this, right? We choose alpha so that the terminal value, the final value of the portfolio is without, or let me say this. The dynamics of the portfolio is without the DWT component. Okay. So again, it's playing along with the idea of getting rid of the risk. Okay, getting the exposure to the DWT. So in other words, actually, is this. So you choose the alpha T, exactly. It's very similar to what we did above, but here you do the alpha T so that the change in the portfolio is only like this. It's only like this. Okay, whatever that is, that thing is inside. Okay, something. But the point is, there's no DWT component. Okay, no DWT. Okay, and so the point that we want to make is this: that if there's no, right, since there's no DWT component, the return, okay, the return. So what is the return on this portfolio, right? The return on this portfolio would be like this, right? Would be whatever that something is, divided by pi t dt. Okay. And the point is, when a portfolio, right, or when something has no Brownian motion component, meaning it's not subject to the risk, then whatever this something is must be the risk-free rate by no arbitrage argument. Is that okay? So is very much like what we've done so far. But what we've done so far is assuming, right, that the Black-Scholes PD holds, and then we deduce something about the rate of return of the portfolio. We kind of turn the picture around and say that, well, if we get rid of the Brownian motion component, then the rate of return of the portfolio must be the risk-free rate, which is R, right, to begin with, and nothing else. Otherwise, there will be arbitrage opportunity in the market. Okay. Now, so why is that the case? So actually, right, is almost the math is exactly the same as what we've done before, except that, you know, we stop somewhere here where we do not know that these guys cancel out. We just kind of lump them together and call that, we call that, you know, something, all right? But the point is this, that whatever that thing is, right, if it's not R in the end, then you have created another risk-free instrument, right? Because by risk-free, we mean no Brownian motion component. But you have created a risk-free component whose interest rate is more than the current rate. So if that's the case, then no one would want to hold the money market account. No one would want to use the bank, right? They would want to use your portfolio. So that's not possible. On the other hand, right, if somehow you achieve a rate that's lower than the interest rate, then you just turn your portfolio around by shorting it. Then you will achieve a higher rate, right? By buying, you know, by borrowing or rent, lending, whatever. So the point being is, right, that if your portfolio completely is risk-free, then the rate of return must follow the risk-free rate of the market. Is that okay? That's the argument here. Okay. So, all right. So so basically, Black-Scholes PD is almost implied by what we've done so far above. It's almost implied by the no arbitrage argument. So repeating, right? So basically, exactly the same as above. So you know what? Just to be lazy, all right? I'll do -1 share here, just exactly like above. Okay. So alpha t in this case turns out to be the delta of the stock, just exactly like above. Okay. So following exactly the same derivation, what we get, right, from exactly what we get is d pi t, okay, is equal to this whole quantity right here, okay? D pi t is this whole quantity right here. So okay, and what do I have? Plus RV, and then minus theta t minus delta t rs minus 1/2 gamma t sigma square st square, this whole thing dt. Okay, so that is what I mean by this something. Okay, so almost like what we've done before already there. So the point is observe this. All right, that's why I say that the whole key to this kind of model is the Brown motion component. It is the risk component itself. Without that, right, without the DWT component, then you can say that all instrument must have the rate of return R. Otherwise, there'll be arbitrage. Okay, so so this, right, this has no DWT component. So by what we said above, right, you see, basically the something, right, this something must be pi t times R. Oh, sorry, right? Why do I have dt in here? Just pi t times R. But if it's pi t times R, then this whole thing will have to be 0. So RV minus theta t minus delta t R S t. And that's the end of the story. Okay. So basically just one step away from what we did above, by observing that without the Brown motion component, you must have the risk-free rate of return. And that's it. Question on this? Yeah, so it comes from here. It comes, remember, after you do the delta hedging, then the ST part cancel out, and you only have this. Where beta, right, is the cash position. Yeah, right. And so then the cash position just get replaced by exactly whatever that is, you know, that perfectly balanced portfolio. So that somehow, right, because it is related to the portfolio value, pi t R goes out, come out of that. All right. So all good there? Any question? All right. So let me tell you, right? So this is all a bunch of like theory and stuff. I think it's really worth it to see it, right, for yourself. But in terms of like, you know, what you will have to do on the homework and exam, that kind of thing, I guess exam is what you care about, right? It's not really about proving any of this theoretical stuff, all right? But what I want you to be able to do is to master or to implement the Black-Scholes PD with different, you know, derivatives. Whoops. For example, let's say, you know, show that the Black-Scholes PD hold for, I don't know, let's say the butterfly spread. Meaning that, you know, I know that it holds abstractly. I don't care about that. I prove that. Like you show me some concrete argument on why for the particular butterfly spread it holds. Another one actually is something we have not done before, is something called digital option. A digital option is something that pays $1 if the stock price goes above some level and pays 0 otherwise. Okay. So it's almost like, right, a call option, except that it doesn't pay ST minus K. It just pays you $1. Doesn't matter how much you go above the level, strike level. So show Black-Scholes PD hold for digital option. So, right, what I expect is something like, what you need to do is to be able to compute the Greeks of these options. I mean, you could, you can quote the formula for the call option without proof, the call Greeks without proof. And then plug those in and show me that is indeed equal to 0. All right, so I'm going to ask you to be responsible at the computational level to check that the Black-Scholes PD hold for these things. And of course, right, you have access to the call option Greeks without proof. So all you have to do is to relate the call option Greeks with these instruments in some way, and then show that it holds. And that's really it, right? Appreciating the Black-Scholes PD and the concept behind it is very important, but that's not going to be part of the exam. All right. Any question on this? So I think this wraps up what I want to discuss on derivative for this class in terms of stock. We have 2 classes left, right? And we will move on to discuss interest rate modeling, okay, and interest rate derivative. So that's going to be the topic for the 2 last classes. I think we have like 8 minutes left. I don't want to start a new topic on 8 minutes. So I think we're going to finish early today, and then pick up for the new topic, interest rate model on Friday. All right. Okay, cool. Thanks for coming. I will see you on Friday then. Thank you, Dylan. Yep, you too.
Oh, thanks, Chip. You're